Welcome, everyone. Happy freezing cold day. I'm glad to see you survived and you made it here. I can't wait for spring. This is rough being this cold, but we'll get through it. Okay, today we are wrapping up chapter 4, looking at batteries. We're going to look at some examples of interesting batteries, see what's going on with our current understanding of redox chemistry. Next class, go ahead and bring a coin. You're not going to spend it. You can go away with it afterwards, but bring a coin for next class. Science Rendezvous is looking for volunteers. This is a really fun activity in May. It's something that I often go to with my kids, and it's a lot of fun. It's a huge event, so if you're interested in applying some of your science, you can do that. Okay, we were introducing the lead-acid battery. Something that's been around for a really long time for good reason. This battery is very robust. It can go over London, Ontario potholes without breaking. It can get through the cold weather that we have today and usually still work. And even on warm days, it can work as well. If we connect 6 of these 2-volt cells in series, then we can get an overall 12-volt battery. And as the name implies, lead acid, those are the components inside this battery as well. And with our understanding of redox chemistry, we can analyze this battery. When it is discharging, that means that it's working spontaneously. We set it up, we connect the electrodes, and the current flows. We have lead, spongy lead, as the anode, and lead dioxide as the cathode. And these plates are lined up, kind of stacked around one another, and then they're immersed in a 2-molar sulfuric acid solution. So that means if this spills, don't touch the solution because it's a strong acid. Now we can analyze what's happening here when it is discharging. Lead is going from an oxidation state of 0 to an oxidation state of +2. Sulfate, SO4, is a polyatomic ion with a 2 negative charge. Therefore, lead must have a +2 oxidation state. If lead is being oxidized, then this is the anode. And then we also have lead dioxide. The oxygen has a -2 oxidation state. Lead, therefore, is +2. That is wrong. That's not +2, that is a +4. Because oxygen, there's 2 of them. 2 times -2 is -4. We need a total of +4 to counteract that -2 and -2 from the oxygen. Lead is going from +4 down to +2. And this must be our cathode, where the reduction occurs. Cathode minus the anode, we find that difference. So 1.7 minus -0.31, which turns into +0.31, and that gives us our cell potential of 2.01 volts. It's slightly off because I said 2 molar, it's actually about a 6 molar sulfuric acid solution. So the concentration is just a little bit different, but this gives us our approximate 2-volt cell. This is when the battery is discharging, but this is a secondary battery. It can also go through a recharge. So my question for you is, based on this reverse reaction, how can we classify this reaction? This is what happens when we recharge the battery. So log into iClicker and submit your answer. Compare your answer with the person beside you for about 30 seconds. And 10 more seconds. And 3, 2, and 1. Okay, we were quite split over here. The answer is B, but let's see why that is the case. Is this a reduction half reaction? Well, reduction happens in this reaction. Lead with a +2 oxidation state is being reduced to lead 0, but that's only half the story. It's a reduction and it's an oxidation. This is a redox reaction. So we can't just say something's being reduced. We can't just say something's being oxidized. This lead sulfate is being both oxidized and reduced, which is the definition of a disproportionation reaction. If you remember back to topic 4.1, we balanced a disproportionation reaction, where it looks like one reactant is being both oxidized and reduced. This happens because we don't just have one compound. We have billions and trillions and moles of compounds. Some of them are oxidized, some of them are reduced. If we go back to the anode and cathode, the half reaction for reduction, the half reaction for oxidation, we can see that they produced the same product. They both produced lead sulfate during the discharge reaction. That's how this turns into a disproportionation reaction. They both made the same product going from left to right in the discharge reaction. So if we wanted to go backwards, we would just be starting with lead sulfate to produce lead and lead dioxide. It's not a voltaic cell when it's recharging. It's acting as an electrolytic cell. Voltaic is spontaneous. Electrolytic is not spontaneous, but we come along and we apply an external voltage to drive those electrons the way that we want them to go. And here is a battery charger. If your car battery dies, if you left the light on or the door open, or it's just getting really old and it needs to be replaced, you can come along and apply just more than that 2 volts times 6 in a series, so 12 volts. Come along and apply just more than that, usually around 14 volts, and that can drive this reaction backwards to recharge the battery. This is the lead acid battery, and we can plot it with its watt hours or its power to kilogram, so the mass, or per liter for volume. You don't need to memorize this, but this is just a nice little bubble diagram. Lead acid batteries are bulky. They're big and they're heavy and they're sloshy. We obviously don't want that for our cell phone. We want something that has more power per unit volume. So we have the same power but in a smaller package. And it's also kind of heavy for the amount of energy you get from it. So again, if we go up to our lithiums, that's where we're going to be getting today, we can see that they're more energy dense. They're also more expensive. So we need to choose batteries that match the application. We want to consider cost, we want to consider environmental considerations as well. Well, lead acid battery was one of the first rechargeable batteries. It's really old, it's robust, it works. Nickel cadmium batteries were one of the first rechargeable batteries, secondary batteries, that could go in like a AA size. These came out in like the 1970s, 1980s, and you could put them in your toys. I grew up partly in the 1980s, and we had, it was really cool at the time, rechargeable D batteries. And I had this little toy, this math toy, that I could put the rechargeable batteries in. But we had to be really careful when we were recharging the batteries. We had to completely use up the battery, and then put it in the charger, and you'd watch it like all day. It was really exciting. And then the light would change, and you could put it back in your toy. But you had to wait for it to be fully used up, and then wait for it to fully recharge before you could take it out of the charger. If you didn't fully discharge it and fully recharge it, the battery lasted less and less time as the years and the months went on. It had this kind of funny memory effect. Well, batteries don't have memories, right? They're not people with brains. How does this memory effect make sense? Well, scientists have discovered that it was actually a buildup of crystals on the surface of the reactants, on the electrodes. So some of the reactive areas were being obstructed as the battery was charged and recharged and used over and over. But a full recharge, a full discharge helped to mitigate this memory effect. But it still wasn't perfect. Based on our understanding of redox chemistry, we can analyze what happens in this nickel-cadmium battery. Cadmium, a toxic metal, can go from a 0 oxidation state to a +2 oxidation state. And of course, a 0 to +2 means it's being oxidized and produces some electrodes, or electrons. Those electrons can then be used up at the cathode, with nickel going from a +4 oxidation state to a +2 oxidation state. And we can write the overall discharge reaction. This is what happens spontaneously when you put it in your toy or your tool. When you want to recharge it, you apply voltage, just more than the cell potential, and you can drive it backwards and recreate your starting materials so that you can use it again. So this was really valuable. This was a really great invention, but cadmium is toxic. So it's not really an ideal long-term, large-scale use battery. So what you'll more often see now is the nickel metal hydride battery. Now, this example, I'm going to put it on OWL. It's asking for a charge and a current and a time type problem. We chatted about these concepts in topic 4.3. So I'm just going to let you solve that one on your own and look at OWL for the answer. So you can find this under lecture materials. We have a recording of our lectures, we have our annotated lecture notes, and some of these extra examples so that we can make more time for iClicker questions and other topics for discussion. So an improvement over the cadmium battery is the nickel metal hydride battery. Let's look at the nickel part first. At the cathode, we have nickel going from an oxidation state of +3 down to an oxidation state of +2. So it's being reduced. At the anode, we have some type of metal alloy, some type of metal mixture, and it's going from a -1 to 0 oxidation number. But what is this metal? Well, it's kind of a proprietary secret. It can be a combination of different metals like lanthanum and neodymium and cerium and nickel and manganese and aluminum. It's a combination to give the overall redox reaction. Now, this battery can also come in a jelly roll style. So again, you don't need the 2 beakers with the salt bridge and the electrodes, but those components are still here. We still have an electrolyte that acts as the salt bridge. We still have the anode and the cathode, and then they're just layered, but they're separated by the electrolyte separator. And then you can roll it like a jelly roll so that you have lots of contact between these 2 electrodes, but it's a controlled design. This is great because it doesn't have toxic cadmium in it. It doesn't have the same memory effect issue. And these nickel metal hydride batteries you can find in a lot of tools nowadays as well. It comes in like standard sizes, like a AA or whatever size that you're interested in. Well, let's get to the one that we probably all have with us today. And this is the lithium-ion battery. This one, as we know, for the amount of power and its application, it's relatively lightweight, has high energy density. We get the energy that we want in a small volume and a small mass. The balance to that is that it's relatively expensive to purchase, but that's okay. It works quite well, and new lithium-ion designs are coming out and being engineered. Well, at the anode, this is a different setup of battery. So conceptually, it's slightly different. We still have some redox components, but here we actually have the lithium ions migrating. intercalating between these anode and the cathode. So let's look at the anode. Here we have on the left layers of graphite, like in your pencil. So that is sp2 hybridized carbon in sheets, and these are the sheets of the graphite on the left-hand side. On the right-hand side, we have the cobalt oxide material, and this is our cathode location. And both of these are anchored, that's why I drew in these lines here, and separated by an electrolyte. Now, if it's a liquid electrolyte, we need to make sure that the anode and the cathode don't touch, or that could short circuit our battery. It could be separated by a polymer type material just to keep those two sides separate. So to illustrate what's happening, here we have the lithium cations, and their electrons can be dispersed in this graphite. I need 10 volunteers to come up and be the lithium cations and the electrons. All you have to do is be able to walk or run at the front of the room. So put up your hand if you're interested in being a volunteer. At the back, 1, 2, 3, 4, 5. Over there, 6, 7, yes. 8 in the red sweater, 9, and 10 in the yellow jacket. Okay, you are a lithium cation. You are the electron for this lithium cation. You are a lithium cation, and you are the electron that goes with this lithium cation. You are a lithium cation, and you are the electron that goes with that one. And you are a lithium cation. Here's your electron, so you stick together. And let's see if I counted correctly. I didn't count correctly. Lithium cation and electron, and you're going to be the power voltage, okay? So you stand here. I need all of my lithium cations and electrons over to this side here. This is going to be our design that we're following. So this is the graphite material. Right now we have our lithium cations and their corresponding electrons. The lithium cations are kind of interspersed between these layers of graphite, and the electrons really like hanging out in the delocalized pi structure of the graphite, okay? Now, in a moment, we're going to set this up, and spontaneously, we are going to have the lithium cations migrate, so that means they're moving. They're going to walk slowly from the anode over to the cathode. You're going to get out of the graphite layers and come on over to the cobalt oxide layers. When that happens, the electrons are going to go through the external circuit that causes the flow of electrons. So the electrons have to go this way around the table. The electrons move faster, so they're going to have to run and meet up over here with their lithium cation, okay? The electrons are actually meeting up with the cobalt oxide, but this is the big idea. Okay, so on the count of 3, the lithium cations intercalate or migrate this way. Electrons run around. Ready? 3, 2, 1, go. Excellent. Yes, right here. This is going to be our design here. Perfect. Okay. Spontaneously, we just had our lithium ions intercalate over to the cathode, and they've met up with the electron, and the electron is going to help cobalt be reduced. That's great. But we need to recharge this battery. It's the end of the day. I need you to come along, and you're going to power up this battery. You're going to apply voltage and drive it backwards. That means you're going to drive the electrons running this way and the lithium cations to intercalate over here. Ready?
Yeah.
Set, go. Excellent. Your phone is now recharged. We're going to plug it in and we're going to use it. One last time, lithium cations intercalate and electrons run. 3, 2, 1, go.
This is a big workout.
And let's just charge it again. Ready? 3, 2, 1, drive these electrons backwards. And well done. Give them a hand. Thank you.
Thank you.
Thank you very much. Thanks. You can put these in here.
Thank you.
Thanks. Thank you. Thank you. You guys rocked it. Okay, well done. So these lithium cations simply migrate over to the other side. So the lithium cation with their electrons are migrating. This electron combines with the cobalt that has a +4 oxidation state that goes down to a +3 oxidation state. So the cobalt is reduced. The lithium cation migrates back and forth. So it's a pretty neat design. Now, the voltage depends on what this cathode material is over here. This was cobalt oxide, or lithium cobalt oxide. This would give about a 3.7 potential difference. But if we used a slightly different material, you can get slightly different voltages. And this is how the lithium-ion battery operates. It's based on redox chemistry, but with some extra little interesting bits like migration. Well, you may remember a number of years ago, lithium-ion batteries heating up and catching fire. I don't expect you to be able to read this. If you want to read this after class, you're welcome to. You don't have to. From Chemistry and Engineering News, it's an interesting infographic on what happens. Lithium-ion batteries, especially the earlier versions, if they got dropped or bumped or overheated, the separator between the anode and cathode could get broken. And this could cause a short circuit and really fast movement of the electrons in the lithium cations, and it can cause it to heat up. And there are some flammable byproducts in this process, and it can cause the battery to catch fire. Now, there are much more stringent rules on designing these lithium batteries, much better designs and circuitry and controls, so it's not as much of an issue now. Lithium cation batteries, there are also versions with the polymer design, and this is just allowing more interesting geometric shapes for these batteries. If we have a polymer material, we can get that anode and cathode nice and close together, but without worrying about the anode and cathode actually touching one another. It's another option to a solid phase electrolyte to keep these items separated. Okay, so that wraps up our conversation on electrochemistry. We started with oxidation numbers and balancing, but now we can see how this matters for batteries, how this matters for a whole bunch of important industrial reactions. Which brings us to our next chapter. And this is our final chapter. I know it's exciting. Okay, and 3, 2, 1. Thank you. Okay, we're a big room, so you just need to keep those side conversations down so everyone can hear. In chapter 2, we talked about thermochemistry and thermodynamics. And chapter 3, we talked about equilibrium, and we actually were able to relate delta G and the equilibrium constant K. And then in chapter 4, we looked at electrochemistry, and we could calculate cell potential, which we could also correlate to delta G. This doesn't correlate to delta G. Delta G tells us, the net difference in energy between the reactants and the products. And we're going to talk about the delta G a little bit. But rates is different than the overall thermodynamics. Rates tells us how fast or slow we are to get there. Some reactions are really fast. Some are relatively slow. And there are some factors that we can control and some factors that we can't control that change the rate of a reaction. What affects the rate of a reaction? Well, the first one is quite generic, and we just call this, the nature of the reactants. Combustion reactions are fast. Acid-base reactions are fast. Carbon graphite with sp2 hybridized carbon turning into diamond, sp3 hybridized carbon, you're going to be waiting a really long time. Basically, don't wait. If you're planning to have a diamond ring in the next 20 years, don't just start with a lump of coal. It's going to take way too long. Very, very slow. And this just depends on the nature of the reactants. We can't control this. But then there are some components that scientists and engineers can control, one being the concentration of the reactants. If we have a higher concentration of reactants, there are going to be more collisions, more opportunities for a reaction to occur. For some reactions, increasing the concentration of the reactants can increase the rate of that reaction. This is what we're going to talk about in topic 5.1, seeing how concentration impacts the rate of the reaction, which depends on the rate law, which is what we're going to talk about today. Then we can also consider temperature and a catalyst, and we're going to talk about this in topic 5.2. I had to clean up my fridge yesterday because we had a little bit of food that had gone bad. But the fridge helps to keep my food less bad. It slows down the rate of decomposition of my food. We can lower the temperature of our food, and it slows down the rotting reactions that are going to happen in your food. In contrast, we can heat up a reaction to make it happen faster, and that's something we can change. Body temperature, there's only so much fluctuation in there before your proteins start to unfold and you have some other serious side effects from temperature adjustments. So in our bodies, when you get a fever, your body is increasing the rate of the reactions by giving you that fever, and it can help to fight whatever infection you have. But our bodies also have catalysts. This is something that is not used up in the reaction, but it helps the reaction to occur way faster, often like thousands or 1,000,000 times faster. You have catalyzed reactions in your body right now that if you didn't have those catalysts, we would all be dead in a matter of seconds. We have lots of reactions happening in our body that don't happen fast enough on their own, but with very special catalysts, often in the form of a protein or an enzyme, they happen faster. So we want to talk about rates of reaction, what it means, what it is, how to predict the rate of a reaction, how to interpret the rate of a reaction, and then we're going to move on to how to manipulate the rate of a reaction through temperature and concentration and catalyst. And then next week, we're going to wrap up with reaction mechanisms. See how learning what a rate of reaction is, what the rate law is for a particular reaction, how it actually gives us a secret insight into the atomic level of what's happening. We can actually predict a reaction mechanism based on the rate law and connecting that rate law to what's happening at the molecular level. So we need to start with a basic question. How do we measure the rate of a reaction? If we want to know if something's happening fast or slow, we need to measure that in some way. And as scientists, we want to be careful the way that we measure it to be strategic and make sure that what we're measuring is actually what we want. Does anyone have an idea on how we could measure the rate of a reaction? How fast something is being used up, or how fast the product is being produced? Any ideas on how experimentally we could do that? I have a microphone. What's one way that we could measure the rate of a reaction?
One way you can measure the rate of the reaction is through temperature, because some reactions will change in temperature, and you can monitor the change in temperature and relate it to the concentration of the consumption or the production of different products or reactants.
Okay, that's a really interesting idea. I love that idea, because we do have exothermic reactions and endothermic reactions. That's a really interesting idea. But we're also going to see in rates of reaction that the net energy or the net temperature change doesn't tell us how fast or slow it happens, unless you can see that temperature change really fast, and then that's a really interesting idea. Maybe we could try that. What else? Another way that we could measure the rate of a reaction. I'm going to come through here.
So one way we could do it maybe experimentally was to, if we were looking at a certain concentration of a product and we could link that to maybe a color change, we could use spectrophotometry to measure the concentration change over time.
Excellent. Put up your hand if you did a spectrophotometry experiment in the last couple weeks. Hopefully everyone. Yes, you are measuring color change. And if we're producing something that is green or pink, you can measure the rate of that particular wavelength increasing or decreasing. It's being used up. Any other ideas on how to measure the rate of a reaction? We have color change, yes.
If it's a gas, then we can use pressure change.
There we go. If we're producing a gas, we could measure the pressure change. So the atmospheres that are going up or down. Yes?
Observing product formed.
That's right, observing product formed. So perhaps if the product is a precipitate, a solid, we could measure the opacity of the solution. We can see through it when we don't have the solid, but then when the solid precipitates and it's all dispersed, we can't see through it anymore. And we could measure that with spectrophotometry as well. Any other ideas? Okay, so we have color changes, gas formation. Gas formation could be maybe pressure, or if it was at the same pressure, we could measure the volume of gas being formed. We could perhaps measure conductivity, any way that we can measure amount that's used up and disappears, or the amount of something forming. The rate of the reaction also depends on what we're talking about. Let's look at this balanced reaction with nitrogen, hydrogen, and ammonia. We can see that this is a 1 to 3 to 2 molar ratio. So let's imagine that this experiment happens in 1 minute. These aren't actually realistic numbers, but let's pretend. In that 1 minute, let's imagine that the amount of nitrogen went down by 1 mole per liter. Well, I could tell you the rate of this reaction based on using up 1 mole in 1 liter of nitrogen. I should also tell you that rate needs to be a positive value. So if I lose 1 mole of nitrogen, I've lost 1 mole per liter of nitrogen, and we're using a made-up value of 1 minute. But the overall rate needs to be a positive number. So I can't tell you it's negative 1 mole per liter per minute. I want to tell you that it's 1 mole per liter per minute. So I just add a negative sign in front of my negative sign, and it turns into a positive. But then I want to tell you about the rate of the reaction in terms of hydrogen. Well, if in that 1 minute, 1 mole of nitrogen is used up, that means 3 moles per liter of hydrogen would be used up. So I've lost 3 moles, or moles per liter, of hydrogen in that 1 minute. And I add a negative sign because the rate needs to be a positive value. And if I wanted to correlate that to the amount of nitrogen, well, then I would need to divide it by 3 to tell you the overall rate law, because it's a 1 to 3 molar ratio. Or I could measure the production of NH3 gas. In that 1 minute, if I used up 1 mole of nitrogen, I would produce 2 moles per liter of NH3 in that same 1 minute. But if I wanted to talk about the balanced reaction, it would be a half. You don't need to memorize this, but we do need to know how to interpret the rate of the reaction in terms of this component to this component to the overall reaction. If I told you the rate of consumption of N2, you would be able to tell me the rate of production of NH3. Moving forward, when we're talking about the rate of the reaction, we're talking about that initial rate, because the reaction tends to slow down as it uses up the reactant. Well, what is the effect of the starting concentrations of the reactants? This is communicated through the rate law. And this is the rate law here. It's the rate of the reaction, and it's equal to some specific rate constant, K. So let's label that. And based on the concentrations of the reactants, or products, to the power of some coefficient. But when we're talking about rates, it's not the same as talking about the equilibrium constant K. When we talked about the equilibrium constant K, we could look at the balanced reaction and just write out the equilibrium expression. We can't do that with rate. We have to do an experiment, or we have to look at data from an experiment from some other scientist. These exponents here, x and y, must be experimentally determined. So I'm not allowed to simply look at the coefficients and run with that. This rate law is going to be specific for a certain temperature. If we change the temperature, well, we need to come up with another rate law, or at least another specific rate constant, k. This specific rate constant, k, we're going to come back to in, I don't know, maybe 2 lectures. There's a lot of extra information wrapped up in this little k value. We're going to tear it apart and see that it has temperature and activation energy and things like that. But right now, we're going to focus on the concentration. The x and the y, those exponents, tell us the order of the reaction according to whatever reactant or product they're referring to. So x would be the order of the reaction according to A. Y is the order of the reaction according to B. And if we take x plus y, that gives us the overall order of the reaction. So how do we figure out what x and y are? That's what we want to do today. Well, it needs to be experimentally determined. So we need to go to an experiment, or we need to interpret the data from someone who did a good experiment. Let's look at this experiment here with hydrogen reacting with nitric oxide to produce water and nitrogen. There were 3 experiments that analyzed this reaction, and these are all the initial concentrations of hydrogen, the initial concentration of nitric oxide. So for run number 1, the experiment started with 1 mole per liter of hydrogen, 0.2 moles per liter of nitric oxide, and it was determined that the rate was 5 moles per liter per second. Maybe they measured evolution of gases, maybe they measured color, whatever. They did something to be able to come up with 5 moles per liter per second. Well, then they did the same experiment at the same temperature, in the same everything, except for the fact that the concentration of hydrogen was adjusted. They doubled the concentration of hydrogen. They kept the concentration of nitric oxide the same, and lo and behold, the rate doubled. And then the scientists did another experiment, going back to the original concentration of hydrogen, compared to the original, doubling the concentration of nitric oxide, and surprisingly, the rate of the reaction quadrupled. Based on this data, we can determine what the rate law is. We're going to come back to this in a second. We're going to actually determine it. But let's talk about how to interpret this. Then I have a question for you, and then we'll actually calculate it. We want to figure out what this big rate law is. We need to know what the x and the y exponents are. For now, we're going to determine if a reaction is 0 order, 1st order, or 2nd order. Is that x 0, 1, or 2? It is allowed to be a half and other weird things like that. But for the next day or two, we're going to pretend that it's 0, 1, or 2. We have to figure out what it is, and then we're going to see that we can derive some integrated rate laws and solve all sorts of interesting problems once we know what that exponent is. Let's imagine I doubled the concentration. So if the change factor was 2, and I took 2 to the power 0, anything to the power 0 is 1. The rate of the reaction was multiplied by 1, which means no change. If I doubled the initial concentration of a reactant and the rate of the reaction didn't change and nothing else changed, then the order would be 0 according to that reactant. But if I doubled the concentration of A and the rate doubled, well, that means that exponent must be 1. It must be a 1st order reaction. If I doubled the concentration of A and the rate of the reaction quadrupled, well, then it's going to have to be a second order reaction according to A. And we can do this for A and B. So look at this experimental data that we just talked about a moment ago. What is the order of the reaction according to hydrogen and according to nitric oxide? Chat with the person beside you for 1 minute. Okay, and 10 more seconds. And 3, 2, and 1. Okay, most votes for A, but only 63%. So let's see how this is the case. This right here is what I call the hand-waving explanation. I can see that from run 1 to run 2, concentration of hydrogen doubled, nothing else changed. Temperature stayed the same, initial concentration of the reactant stayed the same, everything else stayed the same. The rate of the reaction doubled. The change factor was the same as the change in rate. I doubled the reactant, the rate doubled. Therefore, X equals 1. I'm having trouble writing things down. The same change happened to the reactant concentration, same change happened to the rate. Therefore, it must be 1 according to hydrogen. So X is 1. If I compare run 1 to 3, hydrogen stays constant. Nitric oxide doubled. The rate quadrupled. It increased by a factor of 4. Or the change 2 to the power 2, which gives me 4. That power, therefore, must be 2. For simple numbers like this, we can interpret the rate law reasonably easy with some practice. But sometimes we get more challenging numbers. So this is why I'm going to show you the calculation method as well. We've already determined the order of the reaction as X equals 1 and Y equals 2. But let's calculate that so that we know another technique when we don't get numbers that are easier to do in our head. We can determine the order for each reactant. And we're simply comparing the rate law for one run and comparing that rate law to another run. For simplicity and to solve for X, the order of the reaction according to hydrogen, I'm going to compare run 1 to run 2. I'm going to put run 2 on top of run 1 as a fraction because I like doing math as easy as possible. I love math. Complex math is good. But why do it harder than you have to? I like to put big numbers on top of smaller numbers because then I don't have to do fractions as often. You can do it however you want. It's a math problem. You can do it anyway. But big numbers on top of small numbers is just nice and easy. So the rate law is the rate of run 2. The rate law is K, concentration of hydrogen to some power, concentration of nitric oxide to some power. And I can compare that to rate 1. The rate law is going to be the same if we just have the concentration of A. The x and the y aren't changing by changing initial concentrations. But I can now plug in this experimental data to solve for x. Now we can see the beauty of fractions. The specific rate constant k isn't going to change by changing initial concentrations, so that factors out. These concentrations didn't change, so those factor out. 0.2 to the power x divided by 0.1 to the power x. I can take out that power x as 0.2 over 0.1 to the power x. 10 moles per liter per second divided by 5 moles per liter per second gives me 2 moles per liter per second, which gives me 2 equals 2 to the power x. By inspection, what does x have to be to make this mathematical equation true? Well, x has to be 1. If it wasn't so obvious, I could take a log of both sides, bring that x down, and we could solve it that way. We could do the same thing for y. And I'm going to let you do this on your own time. You could take run 3 divided by run 1. Cross out the things that aren't changing, isolate for y, and you're going to end up with 4 equals 0.4 over 0.2 to the power y, which gives you 4 and 2 to the power y equals 2. We're not done this problem, but we are out of time. So when we come back next class, we're going to solve for k and wrap up this problem. Have a great day. I'll see you on Wednesday.